let me start by saying all of this was motivated by the amount of data that is coming online related to COVID infections and tests and all of that. And there's a lot of variability in the quality of the data, in the data sources. Sometimes people have just stopped sharing data and all of that. And so I thought it would be useful to collect together some more reliable data sources and also to identify typical traps while trying to analyze this data. Because the distributions are not normal or uniform, and most of the times we're just used to putting things into Excel and drawing a straight line. And some of those things may or may not work, and I just want to identify those things that won't. So the toolkit, this is sort of a toolkit for do-it-yourself data science, but most of the tools are conceptual, because there's a ton of data and there's a ton of code. And so it's really important to understand what it is that you want to do and what mistakes people are making. So that's kind of a quick summary. That's about me. And you may have seen this earlier. If you're...
Sorry to interrupt.
Yeah, I got to move this aside, I know.
Someone is saying if you could speak up a little bit, if possible.
Okay, can I, hang on, let me just turn up my mic volume then.
However, I hear you pretty fine. Grace, do you hear Nitin pretty fine?
It sounds very clear.
Okay, so I think Hassan, if you could increase your volume a little bit.
How about now? Is that louder?
Yeah, we hear you fine. Thank you. Sorry about that. Apologize.
No problem. Okay, so you probably read this in the meantime. If you're looking to get started in data science, these notebooks, these are Python notebooks with Jupyter notebooks with all the data in there. You just have to clone the repo, and everything is in the right place, and you can just start it up. I like jazz. I have a German Shepherd who you might hear barking, and I've actually been a cartoonist, and I've also done stand-up comedy in San Francisco. So those are the other interesting pieces of information. So what we're creating here is a toolkit. I'm just putting together a few things that will work together. Probably this will have to wait for another time, but I can quickly walk through some of the things you could do. What I'm going to talk about is data sources, some basic definitions so that when people use jargon, you understand, and also some caveats. And so I'm just going to start with the caveats. Is basically, you're not going to cure COVID using this toolkit. You're probably not going to be able to build a killer predictive model also because the data quality is very unreliable. But these are tools that you could help other people who are domain experts, help them to analyze their data, and also understand all the jargon so that when people are talking, you can ask intelligent questions and maybe formulate questions yourself. But please avoid publishing Medium posts criticizing experts. Now, the most important thing to understand is all the data coming from all the sources is not of the same quality, not necessarily even the same attributes or the level of detail. And even one of the data sources that I will take, which is created by the LA Times data desk, even that has different levels of granularity. So I will talk about that as well. And most of the times you have averages over states and sometimes over countries. And unfortunately, that loses a lot of data because most of the times the way this disease is spreading is that there are hotspots. A person who's infected flies into a country and then infects the people around. But if you take the average over the whole country, that's going to look like a rounding error. But if you take an average over that region, over that county, it's going to be a high number. So it's important to understand the concentration, where the disease is and how it's spreading. If you're a math person or a physicist, then it's like a diffusion equation and or a heat equation, and there are some heat sources, and the heat is spreading all over. And also, if you look at the data, and this fooled me for a bit, you might see something where it's going up and down. And you might think that there is something happening behind that is causing the periodicity. But it turns out that there is a weekly cadence to all of this, partly because data doesn't necessarily get reported every day everywhere. And especially deaths over the weekend don't get reported until Monday morning. So you see a sudden spike at the beginning of the week, and then you see things falling, but that is not intrinsic to the disease. It's an artifact of the reporting. So it's really important to dig deeper when you look at this data, and if at all you want to play with it, to understand all of this stuff. And here's some jargon again. An outbreak is when the disease happens the first time somewhere. And if it's a single case and it's not controlled, as happened in the US, it becomes an epidemic. And then if it spreads across multiple countries, it's a pandemic. And people are talking about whether COVID will be endemic everywhere, that it's like the flu or like the common cold, that it's always present. We don't know that yet. And then the other thing you will hear is the SIR model. This comes up a lot. And this is a model, actually, my opinion alone, is insufficient to capture all of the dynamics of COVID. And I'll talk about that just a little bit more. But this model is based on math and theory that was done about 100 years ago. And people have applied it then to infectious disease. And the idea is that they have three compartments. And there are people who are susceptible, which is basically the whole population. And then some people become infected, and you move them to the infected state. And then they either recover or they die. And so there is something called removed. In other words, removed from the infected and susceptible population, because the assumption is, and again, that is being questioned, the assumption is once you have the disease, you have immunity and you won't get it again, which is really not true of things like flu and common cold. So even there, this model doesn't apply, but people are applying this model. And most of the things, if you actually are reading any papers, you will look, and invariably you will see that based on the SIR model, blah, blah, blah. And so we'll talk about that a little bit. And then you'll get this, you'll get this thing called case fatality rate, which is number of people died divided by number of people infected. Not the whole population, but the number of people infected. So if a case fatality rate is 2%, it doesn't mean 2% of the population is going to die. It means 2% of the infected people are dying, and that's the past. So that's an important thing to understand. And then there is this thing called R0, which is the initial infection rate. And this is a really important parameter. This tells you how many people a typical person infects. And there's a strong analogy between this and when you're doing viral marketing. Because in viral marketing, you have this ratio, and if it's above 1, then you're going viral. And if you're not, then you're not. And basically, it comes straight out of this, which is if it's less than 1, then the exponent isn't, rather the growth isn't exponential. But if it's greater than 1, then it's exponential. And the thing with COVID is that typically the R has been found to be in the region of 2 or 3. They're still figuring it out. And the business about flattening the curve is to try and reduce the number of people that you can actually even physically contact, so that then R is not as high as it would be if everybody was just mixing around. So this thing is important, and we'll see if anybody knows the name Kevin Systrom. He was one of the founders of Instagram. He and his co-founder Mike Krieger, after they've sold the company, recently have created a website called rt.live, which pulls in data from the COVID tracking project. There's something called covidtracking.com, which aggregates data from all over the place. And again, the data there isn't cleaned up. It's just raw data coming from all over the world. And you have to be really careful to make sure that the data quality of whatever analysis you're doing for yourself or for others is well understood. And finally, positive means you have been tested. So a lot of people talk about positive, but you don't know if somebody's positive or not until they're tested. And so typically positive and negative numbers are very strongly limited by the number of tests that you've actually done. If the tests have not been done, then you don't know unless somebody dies and then they say, oh, well, he had COVID or she. So whenever people are talking about various rates, you have to understand that if the amount of testing is increasing, then the number of positives could be increasing just because your denominator is, the amount of testing you're doing is increasing. And yes, proportionally, you're going to find more people. So when people quote these numbers, you also have to ask, what is the test ratio or what is the test rate? And is that going up or going down? Now, if your test rate is going down, but your positives are going up, then you have a serious problem. But most of the times what is happening, at least at this stage of the disease, is that the tests are going up because more and more tests are being created. They're being shipped around. More and more people have them. People have been tested and others are available. And the initial crunch is gone. And so more and more people are being tested. And then there is the thing with positive. And this is a really important issue. And just a couple of days ago, someone, a major scientist or epidemiologist, actually made some statements on TV that they then had to take back. And so let's understand positive and asymptomatic for a second. It's someone who's been tested and who is found to be positive, but is showing no symptoms. And there are a couple of cases, couple of situations or reports that I've seen where, and I think one was in San Francisco General or UCSF, and I don't know which one, but they tested everybody in the hospital because they had to. And then they found that 80 to 90% of the people who were positive were asymptomatic. That means there are people walking around potentially who don't have any symptoms, but who are potentially spreaders of the disease. And that's the way the disease is spreading, because we don't know from symptoms who has it and who doesn't. And so again, the important part is when somebody makes an assertion about asymptotic spread, like this person on TV said, well, asymptotic spread is very rare. Well, let's unpack that. Well, asymptotic spread is very rare because we are not testing everyone. If we tested everyone, we might find that asymptomatic spread is everywhere. But since we don't have enough data, well, of course it's rare because we are really focusing on the symptomatic people because we don't want them to die. So there's a lot of layers of language and jargon that makes all of this very confusing. And so also I want to give you some cautions about how the data can fool you. And typically we are used to looking at distributions of plots like this and think, oh, well, they're all probably from the same distribution. They're going up and to the right, and we can approximate them by a straight line. Okay, that's fine. But the danger is that if we don't have the underlying distribution, we don't have the underlying data, and we just have an average, and we just have some things like an average and a standard deviation or some simple things, then one assumes intuitively that it's some kind of a linear thing, because that's all we've been taught to do, especially in physics and chemistry labs, where you jiggle the ruler until you find the right slope, and then you draw the straight line. And so here's a very interesting thing that is important, and you can look this up. But these are different distributions, all very different shaped data, and they all have the same mean and standard deviation and correlation, all the same summary statistics. So given summary statistics, you cannot say something strongly about what the underlying distribution is unless there is more information, unless you have some samples. So just looking at those numbers, please don't jump to conclusions about anything. So this is one. And then, you know, the people at Autodesk, this is all from Autodesk research. The people from Autodesk decided to have some fun, and they went even further, and they took a shape of what they called a datasaurus, and then they mixed it up with all this other data, and then they created all of these different distributions, and yet all of them have these summary statistics. So as you can see, you can say nothing about the underlying shape of the data just by looking at these things. So that's the first caution. And the second caution, actually, which is really important as far as COVID is concerned, because data and the behavior of the disease is different in different areas, in different states, Different states have different policies. If we just stick to the US for now, different states have different policies as far as quarantine is concerned, moving around is concerned. And so we have to be really careful, especially about taking aggregate data and looking at it and drawing some conclusions. For instance, this figure, if you look at and do the usual linear stuff, you get a correlation that's negative in this figure. But if you look at smaller stuff, you'll actually see that each of these things has a positive correlation. And each of these could be a region, a city, or something. And if you mix up all the data, then you get probably the opposite conclusion. And this particular phenomenon is known as Simpson's paradox. And it basically shows how if you aggregate data, you can get a trend that looks different from the data at the smaller level. So which is why the granularity of the data that you're looking at with COVID is really important. Otherwise, you get a lot of confusing numbers, and I'll show you those in a little bit. So data and code sources, and so we're going to look at some of these. So the LA Times data source is one that I find, at least from the ones that I have, is the most transparent. Plus, the LA Times is sending people to every county and getting information in real time from each county and updating their data on GitHub in CSV files in extremely detailed stuff, not just at the county level, but at the nursing home level and at the level of agencies and so forth. So you can take their data and then you can aggregate it at various levels and do some experiments with it, which is what I'd encourage you to do. That's a good data source. And in fact, they are often a few days ahead of the state of California when the state of California reports their data. And so I will point out to you where they are and some notebooks and so forth. And then aside from the SIR model, as I pointed out, there is another model, and I've seen some notebooks and a GitHub repo, so I want to point that out. It's called the SEIRS model. And here it stands for susceptible, exposed, and infected. And so that's an important distinction because everybody who is exposed is not infected. Or if you count infected as tested and positive, then everybody who is exposed doesn't show symptoms. Of course, if you test them, they will show positive. And then R is removed. And then the question is, do they become susceptible again after a period of time? Which is why you have to take your flu shot every year because the last year's flu shot won't work. And so it's possible that even if you have COVID and recover, it's unclear until the next year whether you're going to need something or not until the vaccine is around. So this model also captures things that the SIR model doesn't capture. Because one of the things that I saw, and for a while it was a pinned tweet on my Twitter feed, is something that stood out for me is that there's a region in the US of North Dakota, South Dakota, Nebraska, Iowa, Wisconsin, not Wisconsin, just the other four, that had no movement restrictions all along. So there are people moving across, living in one state, going to the other state to work, coming back. And that's where you started seeing all of these meat packing factories or meat packing outfits having large clusters. And of course, these people go home and then they spread it in their neighborhood. So the amount of movement that is allowed is not uniform all over the country. And so you will see different behavior all over the country. And so you have to keep that in mind as well. And if you think of the network of roads all over the country as a graph, a network graph, and the nodes are the cities, then you can begin to think of how this disease might flow around the roads because, excuse me, because say a truck driver or someone who works in another city is traveling around these roads, going somewhere else and infecting them. So you could potentially look at vehicular traffic flow for essential workers as the primary way in which the disease is spreading when everybody's quarantined. So there's a lot you can do if you just think this through on the physical level, and then you look at the data. But if you just look at the data and say, toss it into this huge TensorFlow, something or the other, but not understanding the problem, then you're probably not going to get results that you can interpret very well. You get some numbers, but I'm not sure we will understand what they mean. And so there's also, finally, Kevin Systrom has started modeling RT in different states based on their data and making predictions as to whether that state is going to see an expanded spread or not. I have some questions about that model that I also raised, which is important when you use freely available tools. You also have to look at the assumptions. So if you just Google SIR model and go to Wikipedia, one of the first things that comes up is this stuff, which, as I said, is like almost 100 years old. And that theory led to this model. And then recently I've seen this model. And then there's a Bayesian model. So we'll look at this. I'm not going to get into the math. In each of these, there's a set of differential equations. And then the differential equations get solved and you get some solution. In the SIR model, it's somewhat intuitive. And then it gets more and more complex with more and more variables. So not worth going into it here, maybe in a graduate math class. So there is I'm going to leave this here. This is a YouTube video that shows how the infection spreads. If you haven't seen it, it's terrific. It gives you a visual thing. You probably, everybody's probably seen it. So I'm going to stop for just a second because I saw there were a couple of questions. Should we have them now or towards the end?
Yeah, I think we can probably have them now. Also, would you mind sharing that link into the chats? So
which link now?
Oh, the link that you had in the previous slide.
Oh, I see. This one?
Yeah, I actually personally would be very, very interested in.
Okay, I will share it right now. I click on it and
yeah, or you can do it after. I mean,
yeah,
it works.
I mean, what I can do is I can just take this and put it on Slack. How about that?
Yeah, there are a few questions here. Connor,
okay, go ahead.
We have one question from Neil. Do you need to be an LA Times subscriber to access the data?
No, it's open source up on GitHub. The most important thing in that data source, and which I'm going to then quote here, is the data usage is for informal and non-commercial use only, or for academic research. So that's the only important thing here. And I would have put this data out here on my own thing, but I don't want to, because I want to make sure everybody follows their terms. They're a fantastic data source, and I don't want them to go away because people started violating their license terms. So that's the only thing to remember. This is on GitHub at DataDesk, California coronavirus data. They've got a whole bunch of other stuff there too. Ben Welch is the person in charge of that. He's on Twitter. I've communicated with him a few times. He's very active on putting these results up on Twitter. And in fact, he convinced me to actually subscribe to LA Times to support this. So you don't have to, but if you are subscribing to something, they're doing some good work on this. Then there's the Johns Hopkins Center for System Science and Engineering. Johns Hopkins has been one of the earliest groups, and in general, for other infectious diseases as well. And this is from GitHub. They've got a ton of sources. But again, remember, all the caveats that I said earlier, data source quality, information being lost when aggregating, make sure you're comparing apples to apples. So if you take a region in Italy and compare it to a similar populated region in the US, you're probably not really making a good comparison from a data science point of view, because so many other variables, confounding variables, are probably going to give you confusing results. So if you're comparing neighboring counties, probably a good idea. Or neighboring countries, like in Sweden, they decided to go totally open and go for this thing called herd immunity, where enough people get the disease without symptoms that they become immune, and then the disease doesn't have enough people to consume, and then it kind of stabilizes or dies out. So Sweden went that way, and Norway and Denmark decided to go the more cautious route. And Sweden has now had cases that are like 10x or more the cases and the deaths from the neighboring country. So that's a fair comparison because it's weather, it's everything else is similar, except for the fact that there's a geographical, a political boundary between them. And so you can compare them fairly. But the important thing is to make sure you don't jump to conclusions by comparing data from entirely different areas. And then there is this thing, which is something that University of Pennsylvania has created. It's a hospital model for capacity planning. And this is where I personally don't know whether these estimates, look at this, these estimates are generated using an SIR model. So an interesting exercise would be to take the same data and use the SEIRS plus model and see whether the predictions are different. Because some of this stuff, and I'm not an academic and I'm not an epidemiologist whose life's work depends on this stuff, and lives are hanging in the balance, so it's easy for me to criticize. But I'm seeing some of the times that people are rushing forward without doing just some basic data thinking, that, you know, using older models, using models that may not apply. Again, I'm not an expert, but some of these terms, purely from a data point of view, just stand out. So the SEIR model, and I'm going to go now and look at both what the LA Times data and notebooks look like, but also what the SEIR model looks like. And so here you have susceptible and exposed and infected and recovered, and then this is died. And so each of these has a factor, what fraction of this was exposed and what fraction got infected and what fraction died and what fraction recovered, and how many of the recovered people got reinfected. And so all of these are in a model that they've created. It's quite amazing. It's all in a Jupyter notebook, and it actually includes other things. It gets more and more. The plus is because they've also included what happens when people are quarantined, what happens when testing goes up, and it's a much richer model. And I don't have the bandwidth to apply it everywhere, so I'm hoping people get interested, take the data that LA Times has, and then apply these richer models to the data. And if people are interested in some sort of collaborative thing, you know, I'll be happy to jump in and help. But I think there's a lot of data, and if you do it right, there's a lot of analysis that can be done properly. So the SEIRS plus network model, and this is where it gets interesting, because all the previous models assume that you're connected to people nearby. But as I said, if you imagine the roads to be a network, then you could be able to infect someone 100 miles away because you drive there every week and come back a week later. And so you have these links with some probability that you can infect people far away. And that's, again, more realistic than what we have. So I'm going to take a second and see. I'm going to get out of this and go back here. So what do we have here? So this is where I've gone to the LA Times page. And if you go to their GitHub repo, then this is straight their README, and it has this thing called Launch Binder. And if you click on that, it goes off to this other site that pulls all this information and builds a Docker container and runs this. And so that's what I did. And I'm assuming that because it worked earlier, it's going to work now. And it was quite a coincidence that there was Altair being talked about earlier as well, and these people are also using that. So I'm going to go through this. And what it's picking up is, it's picking up the LA Times agency total. So before we do anything, or maybe you can look at it, I'm just going to go through this. But there is a lot of detailed data in all of these. No, they're still picking up stuff. Okay. Okay. It seems to have died now. So I'm going to go back here.
Is it working?
I think my Docker container must have been removed, so I'm going to start over. In the meantime.
Yes, people are saying, is the Zoom screen supposed to be the LA Times page? I just see the slides.
Oh, you're just seeing the slides?
Yes, we're just seeing the slides.
Huh. Why is that?
Thank you, Todd. By the way, Nitin, you started a pretty depth discussion about COVID in our virtual meetup chat room. So
is that right?
Yeah, there's a lot of really interesting things, you know. So
yeah, that's the real idea. Is like, you know, we got to cut through the noise and do something useful.
yeah.
And so hopefully this one does this. Okay, let's see if this works now.
We can see your Jupyter notebook now.
Yeah, okay, that is the idea. Here's what I'm going to do. I'm going to let this spin up, and in the meantime, I'm going to go over to the SEIR model, which plus model that I talked about. And in this model, so you've got a bunch of things with all of these parameters that you can fiddle around with, and you've got all of those initialized parameters. And the interesting thing is that you can also have checkpoints, which is at what point did the testing start, and at what point did quarantining start, and social distancing start, et cetera, et cetera. So there's a number of these parameters that you can play with and actually try to fit it to your existing data and see if that gives you a prediction. So I don't know if you have time to go through all of this, but all of the links are on this presentation, and people can download it and run it. So what you've got is this tells you what infected, exposed, and I don't know if that is dead or probably is. And this is a percentage of the population, right? And how many days since got infected, how many days since the first case was reported. So I'm just going to be clicking through this, but there's a reference here without isolations, and then if you isolate, what will happen? And you can play with some of this. There's also the network model, and we can go through this. I think I've run it before. This allows, so if you'll notice here, NetworkX is a Python library for drawing networks. But there is this book called, I think, Network Analysis by Barabasi and Albert. And it has a very exhaustive exposition of different kinds of networks with different connectivities and different characteristics. And in all of those cases, you get power law behavior. In other words, a few of the nodes have a lot of the connections, and some other nodes don't have a lot of the connections. And what that gives you is some kind of an exponent. And in some sense, that has relationship to COVID, because connectivity is an important factor for spreading disease. And in fact, isolating people reduces the number of connections between them and reduces the pathways in which the disease can pass. And so I'm going to, since we've gone way over time, right? I'm going to just stop here, but continue on Slack, or if people want to collaborate or learn more. I'm every day talking to people, and in fact, I'm talking to people abroad that have a startup that's actually modeling COVID in different parts of the world. And there are a lot of people doing useful, interesting stuff. So these days, if people have spare cycles, this would be a good way to take real world data and do some data science on it and get it sort of critiqued by your peers.
Cool. We have quite a few questions. We have 5 questions for you.
Okay, go for it.
Great, Connor. Do you want to go ahead?
Yeah, so Jack asks, due to RNA virus nature, we have several types of coronavirus responsible for COVID-19, Asia, Europe, America, etc. And we don't know if people infected with one type immune to the other types. What model is better for such multiple type situation?
Right. I mean, I'm not an expert, but purely from the data point of view, it seems like that the SEIRS model, which allows you to become susceptible again after being infected, might cover this because this is exactly like the flu in this sense, and not in other senses. But in this sense, every season you have different variations of the flu. And so we never become immune to the flu or to the common cold because it's always mutating. So from that point of view, the SEIRS plus model is probably much better than, it's certainly not the SIR model because it doesn't include that.
All right, thank you. I'm going to skip this question. It looks a little bit inappropriate. Sean asks, can we access to the Jupyter notebooks that the presenter is showing us? Can you share the URL?
Yes, so the Jupyter notebooks that I'm showing you have the URLs in the slides. One of them is, all of them are from GitHub repos. So they're all open source, they're all out there, they're not mine. I've collected them and I'm running them on behalf of the people who created them, sort of. So if nothing, at the end of this, I can just put up the links of all of the repos all in one place. But I think I have them in a slide somewhere. So if you're looking for any particular one, like the LA Times one, you look for data desk, all one word on GitHub. And if you're looking for the other one,
it looks like Christopher has been kind enough to link those in the
yes,
chat room.
very
so
good. Okay,
so
good.
For doing that, Christopher.
Okay, so that's one, and then there's also the SEIRS plus one. So if you just Google SEIRS PLUS, SEIRS PLUS, it's like Sean McCormick or someone like that. Yeah, it comes up. So that was it. Two questions. What?
Yep, that is everything.
Okay. Okay, so if we have a couple of minutes, I can just walk you through what Kevin Systrom and guys are doing, just because there is a caveat there, and
Sure.
I will just walk.
If we're set to finish at 9, but yeah, I think you have the remaining time, so feel free. Just leave us 5 minutes at the end.
Yeah, this is good. So
you.
I'm going to. So can people see a new notebook here?
Yep.
Okay. So this is cases. This is of course Kevin Systrom. Fun fact: Kevin was an intern at Odeo, which then became Twitter, where I was consulting when it was Odeo. So I haven't seen him since, but Kevin, if you see this, hi. So anyway, so what they've done earlier what they did was that they used a Bayesian analysis, which is taking stuff from the past and using it to predict the future, and using this model from classical statistics called a Poisson process. And in a Poisson process, it's like calls arriving at a call center, or people arriving at a restaurant, things where you have some place where randomly things are happening, events are happening. Typically, they call it arrival times. And the rest of it is based on the SIR model, again, with all the question marks, and it's also based on the Poisson process. And now the first thing you have to do when somebody suggests a particular model is to just go somewhere, even Wikipedia is fine, go look at the assumptions of that model. And if you go to Wikipedia and look at the Poisson process, the first thing it says is that the assumption is that the events are arriving independent of each other. And fundamentally, that doesn't hold in disease modeling, because especially then, I'm sorry, in infectious disease modeling, because a person is infecting the other person. When you're near a hotspot, they're not independent. They are very strongly connected to each other. And so it's not clear to me how that impacts their conclusions. But I think what it contributes to their conclusions is at a higher degree of uncertainty, because the prediction is based on something that the data doesn't follow. So there's a bunch of things he does, and I'm going to just take you to straight away to the state by state. What they have is, what they're trying to do is to model the infection rate as a function of time, not just the initial one, and then how it has changed in various states. And now you look at California, and if it's gone down and it's rising up again, we can validate that because California is very open about putting up its data. Florida, that simply stopped releasing data, or really controlled releasing data. So this line is, by the way, R equals 1, after which the disease is not exponential, below which the disease is not exponential. So it's hard to believe that that's true in Florida, but we'll find out. And in a number of these cases, the error bounds are very high. And so, again, I don't know how much of this is due to using a Poisson process in the SIR model, but it's important. What I would love for people to help out, because some people have taken these notebooks and applied them to other countries. I would love it if we could collaborate to take this as it is without any changes and just apply it to state by state data in California, and to see how great a predictor it is by looking at just partial data and then see how well it predicted the future. And that would give us, I think, one of the better results, because we have strong confidence, as much as we can have, a strong confidence in the LA Times data set. And we also can do it county by county, or even lower region by region. So again, if somebody wants to do that, I will be happy to jump in and help in whatever way I can. Again, here pointing out, let's not just take some code that's available and slap it together without understanding the math. And one of the things that could be useful is, and I know that there are data scientists amongst the group, that if we could have some group of people mentoring or helping people with their analysis, even if it is just a toy analysis, because it's the same thing as using, I know I don't want to call it stupid, but the stupid iris data set or some other data set which has some 20 lines of data, and then we do all our stuff with it, and it has nothing or very little to do with the real world. But this is real world stuff, and it helps you engage with data in real time, which has an impact. And so if we can educate ourselves in doing data well with this kind of messy data, we can do much better when we have clean data.